Okay, so this is the last assignment that I gave you, which was, I guess, assignment number 8. And the task was you have to connect all these component, which is placed at the bottom layer and under the system on chip. And you can see I've already did that for your reference. So if you try it by your own, you can just compare with your component placement and with your routing, and you can see, okay, have you did the right connections or not, or placement wise is there any difference, or you did the same placement, right? So you can compare and kind of improvise your design if you did that. Apart from that, during this section of layout, I did few changes on the design as well. So I will note down those points first. So on our device section, so this is from the assignment number 8. So what are the changes I made here? So again, as I told you, we had the scope of removing few bypass capacitors. So I did that. So I just removed few bypass capacitor, and I basically not removed those from the schematic, I just masked those, right? So whenever you will be designing the same board in future, or you did the placement and layout for the center section, you can compare, okay, which was the capacitor which I am not using in the design. So the right term will be masked, few bypass caps. Apart from that, the second thing I did, okay, I've added net color on few nets, for example 0.9, 1.8 and 3.3, etc. Okay, so you'll find few power nets which I have added color, so I can able to see, okay, where are those, and so this would be easy when we'll go for the polygon pour on those power nets. Apart from that, I did few changes on the design rule. So what was that? I'll show you that what was the change I did. So I've added, so I changed the clearance. Okay, I've changed the clearance to 0.1 mm. Okay, so that I did because I was facing problem with the type C connection net. So if you see here, so I have to just cross these type C from this one, okay, and I was facing problem with the clearance. So here you can see, I just want to tell you one point. So you can argue with me, okay, Aviral, tell me, are there any chances of clear interference or crosstalk between these pad and this one? So again, how crosstalk works? Anybody wants to answer that? Like, what is crosstalk? Or how interference between the signal works? So when two signals,
magnetic field, the magnetic field, I think, of the track, it affected the other track. That's how it works.
Kind of. So again, what is the meaning of interference and the crosstalk? So it is basically coupling between the signals, right? It is happening because of coupling, right? So when two tracks comes parallel to each other, and there will be coupling of mutual inductance, there will be coupling of capacitive. That is what we called electromagnetic coupling, right? And because of that, some aggressor net kind of affect the another signal, which is the victim net, which is kind of silent, which is not in use during that period of time. So this is what we call crosstalk or interference, right? But in this case, you'll see there is a very small point of you can say clearance issue, right? So I mean, we can avoid that, and there will be this will not cause a potential problem during operation, or because of there is very small amount of area which is parallel with the track, right? So we can do that here. So I did that as well. So where I did that, I can show you. So in the design rules, you will see the clearance section. So I did that to 0.1. Okay. Apart from that, I have added this as well. So the thing I have shown you here, this one. Okay, so I reduce that clearance to 0.064 mm. Okay, so that is the track and SMD pad clearance. This is what I'm talking about, right? So again, instead of doing it for every track, every pad, I did that for the EDP signal only. Okay, because these are the differential signals which is, you know, crossing between these two pads, right? So that you can follow. Apart from that, I did few more changes. Those was okay. So this is the problem that we are seeing from last few sessions, and the fourth change is I've added the net classes on type C, which was kind of missing when we completed the previous assignment. So I can show you that as well. So if you go to the type C, here we go. Okay, this is the connector part. Okay, so here I forgot to add these type C. Okay, and I forgot to add, I guess differential was placed, but I forgot to add the net class for this one. Okay, so this is type C1, and I've added the same net class which is added for the other type C signals. Okay, so it's a signal group net class. Similarly, I did for this type C0. Apart from that, on PCI Express, we placed a wrong net class. So it was HDMI, that was the mistake. So I just correct that, and I just made it all the differential 100 PCI. Okay, so these are the two changes that I did for type C and PCI. So you can tally that as well. On the fifth section, okay, so yeah, that is the thing. Okay, one more thing I did. So if you open the design, so here you can see these kind of cross, right? So what is the meaning of those? I mean, these are the meaning of these is these through hole, you can say this is the mounting hole. Apart from that, whatever the ground via we are using here, you can see. So this, the meaning of this cross is that ground via is connected to the internal layers of ground. Okay, so that means I've assigned those internal layers as a ground as well. Okay, how to do that? So you have to select the layer. So this is the ground plane. Double click on this one, and here you will get the option of like either you have to assign which net you want to assign to that one, and you have to select the ground. Okay, okay, so same thing you can do for power. So again, for power we have to section that, and then we will assign. Apart from that, for other grounds, you can see I've already assigned those, right? So that when you do that, all the ground pads or all the ground vias will be connected to the internal planes. So that one thing I'm going to add here. So what I did, assignment of ground net to internal pads. Okay, so these are the few things that I've added on the assignment number 8. Okay, so before starting, I just want to discuss what will be the assignment for today. So for today, so today what you have to do, you have to just complete all the high-speed tracks routing by following the lesson 12. So on today's session, I will basically tell you how you have to proceed for all the high-speed routing. Apart from LPDDR4, all other high-speed routing is pretty much straightforward. All of them are, you know, kind of directly connected, and you have lot of layers, right? You have 4 number of layers, including top and bottom. So you can use those layers to make those connections. And yeah, and then later I'll share you all the completed this assignment number 9. Okay, so that is one thing. In today's session, we will start from the layout planning. Okay, and majorly we're going to plan the layout for LPDDR4 and RK3399. So as I've already told you, if you go to the PCB section and select the groups, you can see here we have like lot of cross connections, right? So for which byte group we're going to use which particular signal layer, and how it will be routed, that we're going to discuss in today's session. Okay, so before going further, I'm just going to split the screen first, and let me show you few things. So firstly, for the layout planning, okay, so for layout planning, we have to just see where all the byte groups are going on the corners of RK3399. So let's suppose, so this is our RK3399, okay, and here we have LPDDR4s. This is one, this is one, okay, and each LPDDR4, hold on, okay, so each LPDDR4 is divided into 4 sections. So let's suppose this is first byte group, this is second byte group, this is third, and this is fourth. Similarly, this is first, second, third, and fourth. Now how it is connected to this one? So let's suppose, so again we have to select the DDR group 1, okay, and as you can see, it is coming from 3 and going to this section, okay. Similarly, for LPDDR2 RAM, if I'll hold on, okay, now it's visible. So similarly for second RAM, it is kind of similar connection, okay. So it is crossing the fourth one. So if I'll select this, hold on, it is coming like that, right? And how fourth will be connected? So for that we have to select the group 2, and you can see it is crossing the first group that we have selected, right? So it is like this. So I'm going to use next pen. Okay, what is the problem here? So it is crossing like this, and similarly for this as well, okay. Now let's select the third group, and here how it will be connected? So it is coming from here and connected in this section. Similarly for this one, okay. And if we'll see the fourth one, it is, so these are kind of, you know, straight connections. But here the problem is the length for these connections will be really high, right? So we have to plan things accordingly so we can able to reduce the length. So that we will see how to do that. So this is all the byte group connections, okay. Now we will see, now basically we'll do the layout planning. So let's draw the RK3399 one more time, okay. So each corner has kind of 4 sections, okay. If I'll divide each corner, it is 1, 2, 3, 4, 1, 2, 3, 4, okay. And here we have LPDDR4s, just section those quickly. 1, 2, 3, 4, 1, 2, third one and fourth. So where the third one is going, it is here, right? Where the fourth is going, it is in this section. Where the second is going, it is here, and this one is here, okay. Same for this as well. So third is connected to here, fourth is here, this one is here, and all the byte groups, whatever the pads that we are using for LPDDR4, for each byte, all are on this particular section, okay. So like you can't say we have some pads in this section or here, so those are properly defined, and from the SoC side everything is fine. So we have to do the layout accordingly. So here I'm not talking about any particular pad, I'm talking about the whole byte group that we have discussed, right? So in a byte group, what are the signals we have? We have DQ, DQS, and data mask. Okay. Apart from that, we have clock. That is kind of you can say it is divided not as per the byte group. It is divided as per the ranks. Okay. And apart from clock, we have some command and address signals and some control signals as well. So these will route on the different layer because all the layers, so we're going to use, so plan is we're going to use two layers. Let's suppose L1 and L3 for the routing of this LPDDR4 interface. Now let's assign those. So for example, so again, these are the crossing connections. So that means we can't route the third section and fourth section in the same layer, right? So let's suppose I'm going to assign L1 for this one and L3 for fourth. Okay. Now let's visualize all the tracks of the third section is routed on L1. Okay. And for the fourth section, all the tracks are routed on the L3. Okay. So now what will be the layer for this section, which is the first section, which is coming, very closer, or even it can overlap because we have to draw the shortest connection as possible, right? So we can reduce the length. So you can guess what will be the layer for the first section. So it will be L1 again. Why? Because we have, adjacent layer, which is L3, right? So we can't route L3, the first section with L3 layer, right? Because there will be a problem of clearance. There will be, we can't route those tracks on this section. We have to route, we have to follow this way, and which will increase the length, right? Similarly, now we have first section which is routed on L1 layer, right? So similarly, we can't route the second section on the same layer. So that means this will be again L3, and the same pattern will follow for this one because it's similar, right? So this is L1, this will be L3, this will be L1, and this will be L3. Okay. So the reason of doing that is, again, the first thing is length will be reduced, length will be less, clearance will increase. Apart from that, what is next advantage? Yeah, so again, crosstalk, all things comes under the clearance section. Okay, so you can say crosstalk also is a factor. Yeah, another is number of VRs. Okay, so when you route like this, when you will be using two number of layers in this pattern, the number of VRs will be less on the line, because see, this is also a kind of limitation. If you open the, if I'll show you. So you can see here, this is also a kind of design rule. So the maximum allowed VRs for these data groups or the signal groups is 2, right? So that means if we have to change or we have to use the internal layers, we can place one VR closer to the SoC and another VR closer to the LPDDR4 SDRAM, right? So that means there is no scope to place multiple VRs on between the connections, right? So this layer pattern kind of support this, right?
I have a question about the layout requirement.
Yeah.
Where it come from? Where that 2V allowed?
Okay. So again, for RK339, we have only 2 documents, right? One is the datasheet, another is design guidelines. So on design guidelines, they have given all this information for all the interfaces. So what I did, I basically collected those information, in a single document. So it would be easy during the design or when you will be layout all the tracks. So where it is given, yeah. So I've already shown you that during the schematic design, I guess. So here they have given some sample layout as well, how things will be layout, so that we can also compare. Yeah, as you can see here, right? So this is DDR3. If you'll see on, yeah, this is for DDR4, right? So they've given, as you can see here, maximum allowed VI is 4, right? So in this section, see what is the problem with VIA. VIA is the biggest problem for the high speed layout. Okay, how? So again, no one can tell you what is the impedance of VIA, right? So that means whenever we place a VIA which is changing the layer, that is the impedance discontinuity. Okay, so impedance is not which is required as a characteristic impedance, right? So this is kind of obvious. We have to place as less number of VIAs as possible for this one. Okay, so again, the answer is all things are mentioned on the design guidelines. So I've already shown you. Okay, so for all the interface, whatever the number of interfaces that we are using for LPDDR4 or whatever the interface supported by RK3399, all the information is given on this one. This is for LPDDR. Apart from that, they've also given things for other interfaces as well. Okay, I didn't know the exact page number, but you can check from the content. So for example, PCI. Okay, so here they have given the impedance requirement, what will be the skew between the data signals and clock, which RK3399 can tolerate. Okay, so it should be like less than 20 picosecond. So if you have facility to simulate the things, you can verify this as well. Apart from that, if you are following the length matching and proper impedance, this problem will be avoided. Apart from that, what will be the maximum trace length? Okay, what will be the spacing? Okay, so these all things are mentioned on this document only. Okay, similarly they have given the number of VIA allowed for PCI Express. Okay, so I hope you got the answer. Okay, so we were
Okay, thank you.
Yeah.
But sorry, was another question. Is it better to set this rule in Altium, for example, the maximum skew, and this rule? I think it's better to
yeah, so
set
skew properties or whatever the timing rules that is given, you can't verify that during the design or with Altium tool, I don't know. But if you have models, that I will show you like how you can verify those. So that again depends on, so again, where all the timing problems come from, they came from the length matching, right? Whenever the length of a clock signal, for example, we have two components here, right? So again, signal is like a you can say it travels, right? So it travels with respect to time. So like at t is equal to 1 second, it's here. At t is equal to 2 seconds, this same signal will be here, right? So that you also observe, you can observe on the oscilloscope, right? Because on oscilloscope we observe a waveform on a particular, so you'll see a zoom thing here, right, on the oscilloscope, and that waveform will be plotted in this section. Okay, so that means whatever the waveform which will pass this section, it will be displayed on this section, right? So again, it is traveling, right? So that means all the timing problems come from the length, right? And suppose this is our clock, and here I've routed the clock this way. So that means this signal is its length is greater than this one. For example, for this it is capital N, for this it is small l, right? So that means this signal will take greater time, right? So that is what is skew is, right?
Okay, thank you.
Yeah, I hope you got it, right?
Yes, thank you.
Yeah. So yeah, so what we were discussing about the layout planning. So here you can see we have L1, L3, and yeah, we're going to use these two layers for the layout of these both of the LPDDR4, and yeah, and we have also planned which byte group we're going to use for on which layer. So that is one thing.